Usually when we talk about getting like a medical diagnosis, there's this fundamental expectation of just pure precision.
Right. We treat it like engineering.
Exactly. Like you fall off a ladder, you break your arm, the doctor puts you in an x-ray machine, and it prints out that stark, high contrast image, and they just point to that jagged white line on the bone and say, there it is, that's the problem.
It's wonderfully binary. It's broken, or it's not broken.
Mm.
It's a clean, indisputable fact resting right there on the light board.
Yeah.
We find a lot of comfort in things that are completely visible and easily categorized.
We really do. But then you look at how we're starting to rely on artificial intelligence to make decisions, whether that's an AI diagnosing a complex multisystemic disease or, I don't know, a self-driving car deciding whether to brake or swerve at an intersection. Suddenly, that beautiful, clean X-ray machine is just broken. There is no binary.
No, not at all.
If you're listening to this right now and you work with data, or honestly, even if you just use a smartphone, you are living in a world built on a diagnostic landscape that is incredibly stubbornly murky.
It's the absolute definition of diagnostic muddy waters. I mean, when you look under the hood of how these algorithms actually learned, you don't find clean facts.
Right.
You find this relentless, highly unstable tug of war between different types of mathematical failures.
And that murkiness, that tension between us as humans wanting a clean, binary answer and the unbelievably messy reality of the universe is exactly what we are plunging into today. We're going to crawl all the way down into the code to uncover the hidden mathematical gears and the profound, frankly, mind-bending philosophical compromises that literally power modern artificial intelligence.
Yeah, we have a really dense stack of sources for this deep dive.
We do. We're covering statistical learning theory, information theory, and the calculus of probability. We're going to solve the ultimate machine learning tug-of-war, discover why giving a computer more information actually makes it more gullible, and then we're going to look inside the microscopic brain of models like ChatGPT to see how it uses a literal coin flip to keep its artificial neurons from dying.
And if we follow that thread far enough, it leads us somewhere completely unexpected. It actually takes us out of computer science entirely and drops us into an ancient, unresolved conflict between the laws of physical geometry and the laws of probability, all fighting over a single irrational number.
So if you're a data scientist actively trying to debug a neural network that's hallucinating, or if you're just insanely curious about what is actually happening when you type a prompt into an AI, this conversation is going to completely reframe how you view data. It's going to reframe how you view errors. And honestly, it might just reframe how you view mathematical truth itself.
That's the goal.
So let's start with the bedrock, the foundational tension of all machine learning. Let's talk about the tug-of-war between bias and variance.
This really is the starting line. If you don't grasp this specific trade-off, the rest of AI will just look like magic. And it isn't magic. It's an exercise in managing your mistakes.
I love the archery analogy from the sources we pulled for this because it takes this highly abstract statistical concept and makes it incredibly physical.
It really does.
If you're listening, picture yourself standing on a range, holding a bow, shooting arrows at a target. In this physical world, accuracy maps to the concept of bias. It asks a really simple question. Did you aim at the bullseye? If your stance is perfect and your sight is perfectly aligned with the center, you have low bias.
But if your entire fundamental understanding of where the target is happens to be flawed, say, you firmly believe the center is actually the top right quadrant, you're going to confidently shoot every arrow into the wrong spot.
Right.
That is high bias. It's a structural failure in your expectations.
Yeah. Okay, so that's bias. Then we have precision, which maps to variance. Variance doesn't care where you're aiming. It asks, are your arrows tightly clustered together? If you shoot 10 arrows, do they all land in a group the size of a grapefruit? If so, you have low variance. You're highly consistent.
But if your arms are shaking, or you have no established technique, your arrows might scatter across the entire target. One hits the hay bale, one hits the outer ring, one happens to hit the bullseye by pure luck.
Just pure chance.
Exactly. That is high variance. You are completely unpredictable from shot to shot.
Which sets up this wild scenario. You could have a beautifully tight cluster of arrows, like a grouping the size of a golf ball, completely missing the target and embedded in a tree 10 feet to the left.
Yes.
That would be high bias because your aim is fundamentally wrong. But it's low variance because you are incredibly consistent at being wrong.
That is the perfect visualization. Now, let's pull this away from the archery range and ground it in the rigorous statistical reality of machine learning, because the math here is deeply revealing.
Okay, hit me with math.
In any modeling scenario, We have to assume there is a true objective function operating out there in the universe, a set of physical or economic laws dictating how things work. We can call that true function f of x.
The actual perfect rules of the game?
Yes, but we never get to see the perfect rules. We only get to observe the messy outcomes. We see the data, which we call y. And the relationship is always that our observable data y equals the true function f of x, plus a little something called epsilon.
Epsilon, the chaos factor.
It is the irreducible noise. It is the wind blowing your arrows off course. It's the fact that a sensor on a self-driving car has thermal interference. It's the fact that a human being might decide to buy a house just because they like the color of the front door, defying all economic logic.
Right, people are weird.
Exactly. You can never, ever model away epsilon. It is the fundamental randomness of the universe.
So we take our algorithm and we train it on a specific finite set of this messy data.
We do. And our resulting model generates its own predictions. Now, bias, fundamentally, is the model's lack of expressiveness. It happens when the mathematical expectation of your model's predictions, even if you trained it an infinite number of times on infinite data sets, still deviates from that objective reality, f of x.
Okay.
And this happens primarily because of restrictive assumptions built into your algorithm. You assume the relationship between your data points was a straight line, but the real world operates on a complex curve.
So because I forced the model to only think in straight lines, it physically cannot bend to hit the truth. It's aiming straight when the target is moving on an arc.
That is bias. Now, variance is the flip side. Variance is the model's lack of control. It is the mathematical measurement of how much models trained using the exact same algorithm, but on slightly different random data sets, will scatter and twist away from each other.
Like if I train a neural network on 1,000 images today and then train the exact same architecture on a different 1,000 images tomorrow, how wildly different are the two resulting brains? Okay, I have to stop you there because my brain is snagging on something crucial. When I hear the word variance and you talk about it scattering, wait, does variance actually care if the prediction is correct?
That might be the most important question of this entire deep dive, and the answer is a definitive no. Variance has absolutely nothing to do with objective truth.
Nothing. Literally nothing.
Nothing. If you look at the raw mathematical formula for variance, it translates to this. You take the model's prediction on one specific data set. Then you subtract the average prediction that the model would make if you gave it every possible data set in existence.
Okay.
You square that difference so negatives don't cancel out positives, and you take the expected average of that squared gap.
Let me make sure I'm wrapping my head around that. You're saying the formula only compares the model to itself.
Yes. Look closely at what is utterly absent from that calculation. The true function of the universe, f of x, is not in there. The actual observable data labels, y, are not in there. Variance is a purely intrinsic property of the model's stability. It only measures how violently the model reacts to changing data.
That is wild. Think about what that means for someone building an AI. If my model confidently outputs positive 100 on Monday's data and then wildly outputs negative 100 on Tuesday's data, it has massive variance.
Yep.
And that is true even if the actual real-world answer it was supposed to guess was 0 both days. It's just inherently structurally unstable.
It is hypersensitive to the random noise, that epsilon, hiding in whatever specific training data it happened to look at.
I find it so helpful to map these dry statistical concepts onto human behavior. Think about the people in your life or your coworkers. You can categorize human personality types using bias and variance.
Oh, absolutely.
Let's look at high bias combined with low variance.
The archery equivalent of a tight cluster in the wrong place.
Exactly. In human terms, this is the deeply stubborn, heavily prejudiced person. They have so many rigid, unyielding assumptions about how the world works that they completely miss the objective truth of reality. That is the high bias. Their internal model of the world is just wrong.
Right.
But, and this is key, they are incredibly stable. You sit them down, you present them with new data, you tell them a shocking new rumor, and their reaction is totally predictable. They are completely unswayed by the noise. That's low variance.
A perfect mapping. Their rigid internal constraints blind them to reality, but simultaneously make them totally immune to the chaos of the daily news cycle.
Now flip it. Low bias combined with high variance. This is the intensely gullible, highly reactive person. They have absolutely no pre-existing assumptions, no core principles grounding them. Because they are open to everything, given enough time and perfect, clean information, they might actually arrive at the pure truth. That's low bias.
Right. They aren't inherently wrong.
Exactly. But because they have no filters, no constraints, they are easily distracted by the slightest bit of noise. They read one crazy post on social media, and their entire worldview violently shifts. They are chasing the noise. High variance.
Which serves as the perfect bridge into the next massive hurdle engineers face. Let's call it the illusion of assumptions and the God mode paradox. Because once you realize your AI is acting like either a stubborn fool or a gullible reactor, the logical next step is trying to fix those errors.
Right. And if you are listening to this and putting yourself in the shoes of a data scientist, your intuition screams at you. If I know my model has high bias, if it's acting incredibly stubborn and missing the truth, shouldn't I just go in and add more assumptions to fix it? If its assumptions are wrong, I should just give it the right assumptions, right? That feels like common sense.
And that common sense is a brutal semantic trap that ruins a lot of models.
Hmm.
When we use the word assumption in casual conversation, we mean a belief.
Right, like an opinion.
Exactly. But in the rigorous math of machine learning, an assumption means a constraint. It is a mathematical wall you build around the algorithm, physically limiting what it is allowed to learn and the shapes it is allowed to form.
Like the linear regression we mentioned earlier, you're constraining it to a straight line.
Yes, that is a massive assumption. And here is the brutal reality of the universe. Real-world physics, human economics, biological systems, the cadence of human language. These data-generating processes are agonizingly complex, highly nonlinear, and messy.
Yeah.
Therefore, almost any human-made assumption you build into a model is going to be wrong. If the real world is a swirling, complex curve and you force your model into a straight line, it will never, ever hit the truth.
Your constraint literally locked it out of the room where the truth lives.
Precisely. Therefore, to lower bias, you actually have to do the counterintuitive thing. You have to reduce your assumptions. You have to tear down the walls.
Yeah.
This is why we use deep neural networks with billions of parameters. They are highly flexible. You expand the model's physical space so it can bend, twist, and fold itself into any shape imaginable. By removing your assumptions, you lower the bias because the model finally has the freedom to reach out and touch the truth.
But the bill comes due. We just talked about the gullible person. If you tear down the walls, there are consequences.
The consequence is that your variance absolutely skyrockets. When the model has that much freedom, it stops looking for the underlying laws of physics and starts chasing that random, irreducible noise, the epsilon.
Right. It memorizes the noise.
It starts memorizing the exact, pixel-perfect position of every single leaf on a specific oak tree in its training data instead of actually learning what a tree looks like conceptually.
Okay, let's play a hypothetical game. Let's enter God mode. What if I possessed a God's eye view of reality? Say I'm building a model to track the swing of a complex pendulum. And let's say I actually know the exact, perfectly correct Newtonian equations of motion for that specific system. I take those perfect equations and I feed them into the model as a hard constraint. What happens to the math?
If you can pull that off, if you feed a perfectly correct, highly constrained assumption into the architecture, you achieve the absolute holy grail of statistical learning. First, your bias drops to a perfect zero because your model's constrained space now perfectly, mathematically aligns with objective reality. You nailed the bullseye.
Amazing.
And simultaneously, your variance also drops to incredibly low levels.
Right.
Why? Because you've constrained the model so tightly around the truth that it has zero mathematical freedom left to go out and chase random noise. You've locked it onto the signal.
So a perfect assumption is the ultimate cheat code. It fixes both problems at once.
It is a cheat code. But the universe doesn't let us use it. There is a mathematical principle broadly referred to as the no free lunch theorem.
I've heard of that.
Yeah. When we are building AI to translate Mandarin to English, or predict catastrophic weather events, or navigate a car through a chaotic intersection in Mumbai, we do not have the perfect Newtonian equations for those realities. The objective truth is fundamentally unknowable.
Which means we can't provide the perfect assumption? Any strong assumption we confidently enforce is almost guaranteed to be wrong. Okay, let's go to the opposite extreme. If God mode is the perfect assumption, what does an absurdly wrong assumption look like mathematically?
The sources outline a brilliant extreme thought experiment for this. Imagine we build a predictive model and we design it so that no matter what data you feed it, it always, without fail, outputs the number 42.
Oh, the ultimate Hitchhiker's Guide to the Galaxy model. You ask it the price of a house, it says 42. You show it a picture of a dog and ask what animal it says 42.
That is the ultimate wrong, strong assumption. You have constrained the entirety of your model's capability down to a single, unmoving point.
Okay, so let's run the diagnostics on this terrible model. The bias is clearly astronomical. Unless the actual answer out in the real world happens to be exactly 42, the model is completely, hopelessly wrong. It missed the target entirely. But what happens to the variance?
Variance of that model is a perfect, flawless mathematical zero.
Wait, really? Zero variance, even though it's totally broken?
Think back to our definition of variance. It asks, how much does the model's behavior change when you feed it different training data? If you feed this model dataset A, it outputs 42. If you feed it dataset B, it outputs 42. If you feed it pure, unadulterated static noise, it outputs 42.
Oh, wow.
The model is utterly locked in a tiny concrete box. It physically cannot react to noise. It cannot change. Therefore, it has absolutely zero variance.
That is such a powerful way to realize how constraints kill variance. Even a stupid, completely wrong constraint successfully kills variance. But obviously, AI engineers at Google or OpenAI aren't just building models that output 42. How do they actually use this dynamic to their advantage in the real world?
They use a family of techniques broadly called regularization. A common one is the L2 penalty. Regularization is the practice of intentionally injecting wrong assumptions into the model's training process.
Okay, how does that work?
For example, the math might artificially force all the millions of internal weights in a neural network to stay very, very close to zero, penalizing them heavily if they try to grow large.
Wait, I really want the listener to grasp the weight of this. Are you saying that engineers are literally going into the code and making the model perform worse on its training data on purpose? They are intentionally increasing the training error?
Yes, unequivocally. They are willingly, knowingly sacrificing a little bit of accuracy. They are accepting a small, intentional increase in bias, a slightly worse fit on the data the model is currently looking at in order to violently crush the variance.
That is counterintuitive.
It is. But by tying all those mathematical weights down close to zero, they're preventing the model's internal landscape from twisting and spiking too wildly to chase random noise. They trade a small hit in bias for a massive stabilizing drop in variance.
It makes me think of putting a speed governor on a high-performance sports car so the driver doesn't spin out on a wet road. You are physically limiting the top speed of the car. It can't go as fast as it theoretically could. But by limiting it, you ensure the car actually stays on the track and finishes the race when the conditions get unpredictable.
That's a superb analogy. The regularized model won't perfectly memorize the training track, but it will survive the real-world roads. And this constant balancing act brings us to a really dangerous conceptual trap that catches a lot of data scientists. It's the confusion between adding features and adding assumptions, and it leads to the realization of just how blind we actually are when building these systems.
Let's unpack the feature trap. Put yourself in this scenario. I'm building a model to predict real estate prices. I've got square footage, number of bedrooms, zip code. But then I decide to add a completely new column to my data set. I add a feature called, did the homeowner eat breakfast this morning? Now, intuitively as a human being, by adding that column, aren't I adding an assumption to my model? Aren't I hard-coding the assumption that breakfast habits dictate house prices?
It feels like it, but we have to violently separate human motivation from mathematical reality. As a human, your motivation for adding that ridiculous column is because you assume it matters. But mathematically, to the algorithm, adding a feature does not add a constraint. It does the exact opposite.
Wait, how does giving it more data remove constraints?
Because every time you add a feature, you are expanding the mathematical degrees of freedom of the model. You are giving the algorithm a completely new spatial dimension, a new axis to play with. The model is completely free to analyze that breakfast data, realize it has absolutely zero correlation with house prices, and mathematically set the weight for that entire feature to exactly zero.
Ah, it has the choice to ignore it.
Exactly. It is the removal of constraints. You gave it more freedom to explore. Now, if you wanted to force a mathematical assumption, you would use that regularization we just talked about to physically force the breakfast weight to be zero. But simply providing the feature expands the model's universe.
Okay, I see.
And as we just established, expanding the universe lowers your bias, but it provides a million new hiding places for noise, allowing the model to overfit, which causes your variance to skyrocket.
Okay, all of this theory hinges on this concept of f of x, the objective truth of the universe. We're trying to hit the bullseye. But the sources highlight a deeply painful engineering reality. Why is it fundamentally mathematically impossible to calculate your actual bias in the real world?
It goes right back to the equations. Think about variance again. To calculate variance, you only need to look at the model's own predictions across different data sets. It's an internal audit. It compares the model to itself.
Right.
Because of that, variance is entirely calculable. Engineers use techniques like cross-validation or bootstrapping to measure it every single day. But look at the mathematical formula for absolute bias. To calculate bias, you must subtract your prediction from f of x. It literally requires you to subtract the objective truth of the universe.
And if we knew the objective truth of the universe, we wouldn't be building a machine learning model to guess it. We would just write down the formula and go home.
Precisely. Since f of x is the very thing we are desperately trying to discover and we don't have it, the bias equation contains a permanently unsolvable variable. You can never, ever calculate your absolute bias in a real-world scenario.
So AI engineers at the highest levels are just flying the plane blindfolded.
I wouldn't say blindfolded, but they are flying by instrument rating, navigating using shadows. They have to use proxies. In practice, we use the training error. How well the model fits the data, it is already seen as a proxy for bias.
Okay.
If the training error is terribly high, we assume our bias is high, meaning the model is too rigid, we need to tear down assumptions. And then we use the gap between the training error and the validation error, how the model performs on fresh, unseen data as a proxy for variance. If that gap is a chasm, our variance is too high, and we need to add constraints.
It's like Plato's cave. We can't see the true shapes of bias and variance. We can only watch the shadows of training error and validation error dancing on the wall, and we pull levers in the dark, hoping we are balancing the equation. It's incredibly humbling.
It is the reality of the muddy waters. But we aren't completely helpless. If we can't calculate absolute truth, we still need a ruler. We need a way to measure how far off our model's guess distribution is from the labeled data we actually do possess.
Right.
And this brings us into the realm of information theory, specifically looking at tools like KL divergence and cross-entropy.
This is where we need to measure the gap. We have two probability distributions. We have the true distribution of the data we collected, let's call it P, and we have our AI model's approximated guessed distribution, let's call it Q.
We need a mathematical ruler to measure the distance between P and Q. And the ruler of choice in modern AI is often KL divergence, which stands for Kullback-Leibler divergence. It is also known as relative entropy.
The sources dive into the information theory perspective on this, and it is so much more intuitive than just staring at the math. Can you break down the physical meaning of what KL divergence is actually measuring?
Information theory is beautiful because it treats probability distributions like maps. Imagine you need to encode and transmit data across a network. Entropy, just pure entropy, is the theoretical absolute minimum number of bits you need to transmit that information if you are using the perfect true map of reality, which is P.
Right, you can't compress it any further than that.
Exactly. Now, KL divergence measures the penalty. It measures the extra wasted encoding length, the wasted bits of data that you suffer when you try to navigate the real world, P, but you are using the wrong map, your model's map, Q.
So it's a literal, quantifiable penalty for your model being wrong.
Yes. It is a penalty measured in wasted information because your model's expectations of reality do not match actual reality.
But there is a massive trap here that trips up even experienced engineers. When you talk about it as a distance between P and Q, people naturally assume it works like physical distance, like the distance from New York to London is the exact same as the distance from London to New York. But KL divergence is not a true distance metric.
It is emphatically not a distance metric because it is mathematically asymmetrical. The divergence from T to Q does not equal the divergence from Q to P.
If you're listening, try to visualize this with a real-world analogy. Think about trying to navigate a complex city using a GPS map. The penalty for using a map meant for bicycles when you are actually driving a massive truck is completely different than the penalty for using a truck map when you are riding a bicycle.
Let's follow that through. It perfectly illustrates the math.
So if you use the bicycle map while driving a truck, the map might route you onto a narrow dirt walking path or, I don't know, a bridge with a weight limit. You get your truck physically wedged under an overpass. The penalty is catastrophic. It is huge.
Right.
But if you reverse it and use the truck map while riding a bicycle, the map might just keep you on main paved roads and prevent you from taking shortcuts through the park. You've got to pedal a slightly longer route. It's annoying, but you survive. The direction of the comparison fundamentally changes the magnitude of the error.
That perfectly translates to the probability math. In the formula for KL divergence, the true distribution, P, acts as a weighting factor. It heavily, violently penalizes the model Q. If the model confidently says a certain event is impossible, like saying the probability is near zero when the true distribution P says that event actually happens all the time.
That's driving the truck onto a footbridge. Massive penalty.
Yes. But if the model Q predicts an event will happen constantly, and reality P says it's actually quite rare, the penalty is much smaller. It's just a slightly inefficient map.
And there's another crucial property of this ruler called Gibbs's inequality. It states that KL divergence must be non-negative. You can never have negative wasted information.
Right. It is always greater than or equal to zero. It only hits exactly zero if your model's map perfectly, flawlessly matches the true map of reality. The underlying math proof for this relies on something called Jensen's inequality and the strict concavity of logarithms.
Okay, don't lose us in the math jargon. Concavity of logarithms.
Think about the shape of a logarithm curve on a graph. It curves downwards like the roof of a cave. Because of that downward curve, the expected average value of the log is always mathematically less than or equal to the log of the expected average value.
Okay.
When you run the divergence formula and flip the signs, that geometric curve guarantees the final result is always positive. The philosophical takeaway is simple. You can never accidentally compress data better than the theoretical absolute minimum limit of the universe. The universe won't let you cheat entropy.
That makes sense. But here is a practical question. If you listen to AI engineers talking about training massive language models, they rarely say they are minimizing KL divergence. They almost always say they're minimizing cross-entropy loss. Are they just using a different name for the same thing?
They're intimately algebraically linked. Let's unpack the identity. Cross-entropy, which we can denote as h of p comma q, is mathematically equal to the pure entropy of the true distribution, h of p, plus the KL divergence between the two, which is that penalty term.
So cross-entropy equals true entropy plus the KL penalty.
Yes. Now consider supervised machine learning. Say you're training an AI to look at medical x-rays and classify them as healthy or broken. The true labels in your dataset are fixed. The picture of the broken arm is always a picture of a broken arm. The reality doesn't change.
Right.
Therefore, the pure entropy of those true labels, h of p, is a rigid constant. It never fluctuates during the training process.
And anyone who's taken Calculus 101 knows what happens to a constant when you take the derivative. The derivative of a constant is zero. It vanishes.
Exactly. When the massive neural network is calculating its gradients to update its billions of internal weights and learn, that constant h of p term completely zeroes out and vanishes from the optimization math. Therefore, taking the derivative to minimize cross-entropy is mathematically functionally identical to minimizing the KL divergence.
So it's just a shortcut.
Engineers use cross-entropy simply because it is computationally cheaper to calculate for the silicon. You don't have to waste processing power computing the baseline entropy of the true labels over and over every single millisecond.
Oh.
But philosophically, underneath the hood, what the AI is actually doing is minimizing KL divergence. It is desperately trying to squeeze its map to match reality.
This is a perfect transition. We have been looking at the macro-level architecture of machine learning. Bias, variance, the information theory of evaluating errors. Now, I want to take a microscope and zoom all the way down into the micro-level wiring of modern AI. Let's look at the literal brain cells of a model like ChatGPT, and specifically the gatekeeper of those cells, the activation function.
This is where abstract probability theory stops being an idea and physically manifests inside the silicon.
If you look at the architecture of the most massive state-of-the-art models today, GPT-4, Claude, massive vision transformers, they almost all use an activation function called GLU, G-E-L-U. It stands for Gaussian Error Linear Unit. It has largely dethroned the classic champion, which was ReLU. Why? What was wrong with ReLU?
To understand the shift, you have to visualize what an activation function actually does. A deep neural network is a sprawling web of millions or billions of artificial neurons. An activation function acts as the bouncer, the gatekeeper, for every single one of those neurons. It looks at the incoming mathematical signal from the previous layer and has to make a split-second decision. Do I let this signal pass through to the next layer, or do I block it?
And the classic ReLU rectified linear unit was a very simple, very strict bouncer.
Extremely strict. The logic of ReLU is binary. If the incoming signal is a positive number, even a tiny positive number, let it pass through exactly as it is. But if the incoming signal drops into the negative, crush it to absolute zero. Block it completely. No exceptions.
Which sounds incredibly fast and efficient for a computer to process.
It is computationally blazingly fast. But that harsh binary strictness causes a massive fatal problem called the dead neuron syndrome. During training, if a neuron's internal weights accidentally get pushed too far into negative territory, ReLU outputs a hard 0. If the output is 0, then during the backpropagation learning phase, the gradient that flows backward to update that neuron is also 0.
A gradient of 0 means it learns nothing.
Right, the neuron gets stuck. No matter what data passes by, it outputs 0, so it receives 0 feedback. It stops learning entirely. It is functionally dead space in your network. If enough neurons die, your model's capacity to learn collapses.
Enter GLU. How does GLU solve the dead neuron problem?
GLU completely abandons the harsh binary logic of ReLU. Instead of a hard wall, it introduces a probabilistic approach. It takes the incoming signal, let's call it x, and multiplies it by the standard normal cumulative distribution function, denoted as phi of x.
Okay, let's translate that math back into the real world. What is the GLU bouncer actually doing at the door of the neuron?
It is asking a deeply statistical question. It looks at the incoming signal x and it asks, assuming all the data flowing through this network roughly follows a standard normal bell curve, what is the mathematical probability that a random input drawn from that curve would be smaller than my current input x?
Oh, it's sizing up the signal relative to the crowd.
Exactly. If x is a massive, highly positive number, the probability that a random input is smaller than it is almost 100%, or 1. So the signal is multiplied by 1. It passes through completely untouched, just like ReLU.
Right.
If x is a deeply negative number, the probability is almost 0. It gets multiplied by 0 and blocked. But the magic happens in the middle, right around 0. It doesn't just slice off sharply. It acts as a smooth, probabilistic gate.
It's like a bouncer at an exclusive club who rolls dice. ReLU is the bouncer who looks at a clipboard and says, if you are on the VIP list, you are in. If you are not, absolutely no entry. Go home.
Yeah, exactly.
GLU is a much more sophisticated bouncer. If you are clearly a massive celebrity, you walk right in. If you are notoriously bad news, you get tossed. But if you are borderline, just an average person, the bouncer flips a weighted coin based on a bell curve to decide your fate. Sometimes you get a little bit through, sometimes you get blocked.
That is an exceptional way to visualize it. And this probabilistic smoothing provides incredible, tangible mathematical benefits to the network. First and foremost, it makes the function infinitely differentiable. There are no sharp, jagging corners like there are in ReLU. This smoothness allows the optimizer algorithms to glide smoothly down the error landscape during training, finding the minimum of error much more reliably.
But the sources point out something really weird about GLU. It has a strange quirk when dealing with slightly negative numbers.
Yeah, the non-monotonicity. This is its secret weapon. Unlike ReLU, which just hits 0 and flatlines forever in the negative direction, the GLU function curve actually dips slightly below 0 before eventually coming back up to flatten out. Right around the input value of negative 0.75, GLU has a tiny, shallow negative dip.
What is the point of letting a negative signal through? I thought we wanted to block negative signals.
We do, generally. But that tiny dip is a lifeline. It allows a microscopic trickle of negative information to flow forward through the network. And because information is flowing, a tiny gradient can flow backward during learning. It keeps the neuron on life support. It's barely alive, but it isn't dead.
That's brilliant.
It is. If the underlying data shifts, that tiny gradient allows the neuron to eventually pull itself out of the negative territory and recover. GLU effectively acts as a stochastic regularizer. It beautifully blends the benefits of dropout, which randomly turns off neurons to prevent overfitting with the standard gating logic of ReLU.
But wait. If you are a computer engineer calculating a perfectly accurate, continuous Gaussian probability integral for billions of neurons, billions of times every single second, that has to be computationally brutal on a graphics card.
It is way too brutal.
Yeah.
Calculating exact mathematical integrals for the bell curve is far too slow for modern AI hardware. So engineers do what they always do.
Yeah.
They use brilliant approximations.
They cheat.
Pretty much. Instead of doing the pure integral, they use faster algebraic functions, like the hyperbolic tangent tan or the sigmoid function, which is often called the squish activation when deployed this way. These specific algebraic formulas closely mimic the smooth, dipping shape of the true GLU curve, but they run exponentially faster on silicon chips because they only require basic multiplication and division.
It's a pragmatic hack. But if we want to understand the true underlying math of GLU before it gets approximated into a shortcut, we have to look at the core mathematical function it is built on. We have to look at something called the error function, or ERF.
We do. And this takes us into a fascinating piece of scientific history. The formula for GLU relies entirely on calculating ERF of x. For the mathematically inclined, The raw definition of erf of x is 2 divided by the square root of pi times the integral from 0 to x of e to the power of negative t squared, dt.
Okay, let's pause right there. Just the name alone. Error function. Where does that come from? It sounds like the math itself is admitting it's making a mistake.
Not at all. It's not a function of a mistake. To understand it, we have to trace it back to the 19th century. We're talking about giants of mathematics and astronomy, Pierre Simon Laplace and Carl Friedrich Gauss. They were peering through early telescopes, trying to track planetary orbits and map the stars. And they realized a frustrating truth. Human eyes and mechanical instruments are flawed. Their measurements always contain tiny random variations.
The irreducible noise, the epsilon of the 1800s.
Exactly. So they started plotting these measurement errors on a graph. And they discovered that the errors always formed a predictable shape. The bell curve, the normal distribution. Small errors clustered thickly around the true center, and massive wild errors were incredibly rare, tapering off into the tails.
Okay.
The error function was mathematically defined to calculate the exact probability that any given observational error would fall within a specific symmetric range, say, between negative x and positive x. That integral formula we just mentioned is literally calculating the physical area under the bell curve between your chosen boundaries. It is a function that measures the probability of errors.
Okay, I need to put on my amateur mathematician hat here because I have a serious bone to pick with the way this formula is written.
Go for it.
If you look closely at the math for ERF, the core thing we are integrating the shape of the curve itself is e to the power of negative t squared. Now, the constant e is a positive number, and any positive number raised to any real power is always going to be positive.
That is correct. The curve is always above the x-axis.
So the physical area under that curve is always accumulating positively. How on earth can the error function ever output a negative number, yet the sources explicitly state its range goes from -1 to +1? How do you get negative area from a curve that never drops below 0?
This is a beautiful quirk,
Yeah.
and it requires a quick refresher on the geometry of calculus. You were absolutely right that the physical curve of e to the power of negative t squared floats entirely above the x-axis. It is always positive. But remember, a definite integral is not just a static area, it is an action. It has a direction of travel. You are sweeping across the graph, integrating from a starting boundary to an ending boundary.
In this formula, you are integrating from 0 out to x.
Precisely. Now, when x is a positive number, say +5, you start at 0 and sweep from left to right. Because you are moving in the positive direction along the axis, the area you accumulate is positive. But what happens to the action when x is a negative number, say -5?
You are integrating from 0 to -5.
Yes. You are starting at 0 and sweeping backwards. You are moving from right to left. In the rigid rules of calculus, when you reverse the bounds of integration, you must pull a negative sign out to the front of the entire equation.
Oh, I see.
So the integral from 0 to -5 mathematically becomes the negative integral from -5 to 0. The physical area under the curve is still a positive space, but because you swept your mathematical broom across it in the negative direction, the calculus dictates that the accumulated value must be negative.
Oh, it's a directional penalty. That makes perfect intuitive sense once you visualize the motion.
And this directional motion is what makes erf of x what mathematicians call an odd function. Mathematically, that means erf of -x is exactly perfectly equal to the negative of erf of x. If you grab it, it has perfect rotational symmetry around the origin. Whatever it does in the top right quadrant, it does the exact mirror opposite in the bottom left quadrant.
That's the theoretical perfection of calculus. But let's bring it back to the silicon. Computers cannot do theoretical calculus. A CPU cannot look at an integral sign and continuously sweep an imaginary area. How does the machine actually calculate this?
It has to break the smooth curve down into discrete manageable blocks. It does this through infinite series, specifically something called the Maclaurin series expansion. You can take that complex exponential integral and rewrite it as an infinitely long string of simple polynomial terms being added and subtracted.
Like what?
It looks like x minus x cubed over 3 plus x to the 5th over 10 minus x to the 7th over 42 and on to infinity. A computer is very good at basic multiplication and addition, so it just starts calculating those polynomial terms one by one, adding them to a running total until it reaches the required level of decimal precision.
But the sources dedicated a significant section to a major technological danger here, dealing with how computers handle floating point math. It's a phenomenon called underflow.
Underflow is a silent killer of statistical models. Here is the problem. As your input x gets very large, The output of the error function gets extremely microscopically close to 1. It becomes 0.99999, trailing off into infinity.
Okay.
Now, suppose you are an engineer and you need to calculate the probability of a massive long-tail event. You want to know the chance of an error being greater than x.
Hmm.
Mathematically, the formula is simply 1 minus ERF of x.
Simple enough.
It is simple on a chalkboard. But in a computer's physical memory architecture, floating point numbers only have so many decimal places they can hold. If ERF of x evaluates to 0.9999999999999, the computer's memory simply runs out of room to store those nines. It rounds the number up to exactly 1.
And 1 minus 1 is 0.
Exactly. The computer calculates the probability of that rare event as absolute 0. It loses all the microscopic tail information.
Let's put that in a real-world context so the listener feels the danger here. Imagine you are writing the code for an autonomous driving system. You need the car to calculate the probability of an incredibly rare freak event, like a pedestrian jumping blindly out from behind a moving bus in the rain. It's a 1 in a million chance. It's way out on the tail of the bell curve.
Right.
But because of underflow, your error function rounds that 1 in a million probability down to a hard 0. The car literally becomes statistically blind to the event. It decides the event is impossible, so it doesn't bother preparing the brakes.
That is exactly the stakes we are dealing with. And to prevent that catastrophic blindness, engineers cannot rely on 1 minus ERF. They have to use a completely separate, dedicated mathematical function called the complementary error function, or ERFE.
How does that fix it?
ERFE does not subtract from 1. It calculates the integral starting directly at x and sweeping out to infinity. By structuring the math that way, it avoids the rounding error and preserves the microscopic, life-saving precision of those extreme tail probabilities. It's a profound testament to how fragile computational math can be when you push it to the extremes of probability.
This precise issue of how probability accumulates over a curve sets the stage beautifully for another major concept. We need to clearly distinguish between two foundational ways of looking at these probability distributions, the PDF versus the CDS. And in doing so, we are going to untangle a massive mind-bending intuition trap regarding coordinate scaling.
The distinction between a probability density function, the PDF, and a cumulative distribution function, the CDF, is arguably the most frequently misunderstood concept in early statistics. But it is vital for understanding AI.
Let's rely on the water analogy. It's the cleanest way to visualize it.
The water analogy works perfectly. Let's start with the PDF, the probability density function. Imagine a faucet pouring water into a bathtub. The PDF represents the instantaneous flow rate of the water coming out of the faucet at any given millisecond.
Okay.
That flow rate is highly volatile. It can surge up, it can drop to a trickle, it can spike dramatically. If we map this to a bell curve, the flow rate is at its absolute maximum, highest pressure, right at the center point, the mean.
Okay, so PDF is the unpredictable flow from the faucet. What is the CDF?
The CDS, the cumulative distribution function, is the total reservoir volume. It is the bathtub catching the water. Now think about the physics of a bathtub. As long as that faucet is dripping even a microscopic amount of water, as long as the PDF is above 0, the total volume of water in the tub must go up. It cannot go down. Mathematically, the CDS is strictly monotonically increasing. It starts at 0, a completely empty tub, and it slowly, relentlessly fills up until it reaches 1, representing 100% of the probability space.
And the beautiful part is how they are linked by the fundamental theorem of calculus. If you take the integral of the flow rate, if you accumulate all the water over time, you get the total volume, the CDF. And if you run it in reverse and take the derivative, measuring the steepness or slope of the volume curve at any exact moment, it gives you the instantaneous flow rate, the PDF.
Exactly. They are two sides of the exact same coin. But here is where the massive intuition trap lies. It happens when we try to physically scale or stretch these distributions. Let's say we start with a very skinny, tight bell curve. In statistics, that is a normal distribution with a variance of 1/2. We denote it as n, 0, 1/2.
It looks like a sharp spike.
Right. And let's say we want to stretch it out. We want to scale it up into a standard, fat, wide bell curve with a variance of 1, n, 0, 1.
Okay, if you are listening to this, I want you to answer this in your head before the expert does. My intuition, and I think almost everyone's human intuition, screams this logic. If the physical distribution needs to get bigger and fatter, shouldn't we multiply the x inside the function by something? We want the standard deviation to grow. So to stretch it, we should multiply the input by the square root of 2, right? Bigger means multiply.
That is the trap. It is a completely logical thought process, but it is entirely mathematically backwards. And it happens because our human brains conflate the data points with the function coordinates.
Okay, you have to unpack this carefully. What is the difference?
If you want to make the physical distribution fatter, you absolutely must multiply the raw data by the square root of 2. If you have a specific data point sitting at position 1 on the graph, you multiply it by the square root of 2, and it physically moves further out from the center to position 1.414. The data expands outward. That part of your intuition is correct.
Okay, so the data multiplies.
And this is the critical counterintuitive leap when we write the actual mathematical formula f of x. The x inside those parentheses is not a data point. It is the coordinate axis of the graph itself.
It's the physical ruler we are using to measure the space.
Exactly. Let's use a real-world example. A teacher applying a grading curve to a test. Imagine a professor gives a brutally hard exam. All the students score poorly, and their grades are clustered tightly together around a 50%. That is our skinny distribution, n, 0, 1/2. The teacher looks at the cluster and decides to curve the grades to spread them out over a wider range. She announces to the class, I am going to multiply all of your raw scores by the square root of 2. The data expands. The distribution gets fatter.
Okay, the students are thrilled. Their scores just went up.
Now, imagine you are looking at the original grading rubric, the original skinny mathematical function that defines the grades. A student walks to the teacher's desk and says, my new curved score is an 85. What was my original percentile rank on the old scale? What mathematical operation does the teacher have to perform to find the answer? She cannot multiply the 85. She has to take the student's new inflated score, and she must divide it by the square root of 2 to map it backwards onto the original rubric.
Oh, because she has to undo the expansion to find the original location.
Exactly. The function f of x is essentially asking, what original input on my old scale corresponds to your new position? Because the physical data expanded outward by a factor of the square root of 2, the underlying coordinate axis, the x inside the function, must scale inversely. You have to divide by the square root of 2 to look it up on the old map. The golden rule is data expands equals function input divides.
That is so profound once it clicks. Think about stretching a physical rubber band. If you take a rubber band that has inch marks drawn on it and you stretch it out, those ink marks get further apart. The space expands. So if you want to find the mark that says 1 inch, you can't look at the same physical spot you did before. You have to travel further down the stretched band. You have to divide your current physical position by the stretch factor to find the original ink mark.
It is a perfect physical visualization. And this strict inverse scaling rule is exactly why you see division by the square root of 2 absolutely everywhere in probability formulas when they are standardizing a variance. The math has to divide the ruler to account for the stretching data.
And this rubber band stretching sets the stage beautifully for our final act today. This is where all the threads we've discussed, the math, the geometry, and the probability, violently collide. Let's look at the tale of two distributions and the philosophical battle over the square root of 2.
We are going to directly compare two specific geometric shapes here. Our skinny curve, n, 0, 1/2, and our fat curve, n, 0, 1.
Let's paint the picture clearly in the listener's mind. The skinny curve is tall, it's incredibly steep, and almost all of its mass is highly concentrated right around 0. The standard fat curve is much shorter, it's fatter, and its mass is spread wide.
Let's look specifically at the peaks of these two mountains. Remember the unbreakable law of probability.
Yeah.
The total area under any probability curve must equal exactly 1. It represents 100% of possible outcomes. Because the skinny distribution has a smaller variance, its total probability mass is squeezed into a much tighter horizontal space.
Right, it can't just lose area.
Exactly. To keep the total area at exactly 1, the peak of that skinny curve has no choice but to shoot drastically upward. Mathematically, its peak is exactly the square root of 2 times higher than the fat curve's peak.
Which means what, in practical terms? Why does the height matter?
It means concentration of certainty. It means that if a physical process follows the skinny curve, you have a 41.4% higher certainty that any given observation will fall infinitesimally close to the absolute center compared to a process that follows the fat curve. The probability is 41.4% denser.
Now let's dispel a massive visual myth that trips up almost everyone when they first learn statistics. When people picture a tall, skinny bell curve and a short, fat bell curve superimposed on the exact same graph, they almost intuitively assume that the two curves meet or touch right at the origin, right at the very top of the fat curve.
It's an incredibly common visual illusion. But as we just established, they absolutely do not meet at the origin. The skinny curve towers 41.4% above the fat curve at the center. So the question becomes, where do the lines actually cross?
The sources outline the precise algebra for finding this intersection.
They do. If you set the mathematical equations for the two probability density functions equal to each other, and you solve for x, you discover that they intersect at exactly 2 points. Not 1 point at the top, not 3 points, exactly 2. They cross precisely at x equals positive square root of the natural log of 2, and x equals negative square root of the natural log of 2.
Which, if you run the decimals, is roughly positive and negative 0.83.
Correct. Geometrically, it forms a striking image. The tall, skinny curve is completely dominant, towering above the fat curve in the center. But then, as you move outward, right at those two precise intersection points of plus and minus 0.83, the skinny curve crashes downward exponentially fast, literally piercing through the ceiling of the fat curve from the inside out.
That's a crazy visual.
In the long tails beyond those points, the fat curve actually rests on top because it has more of its probability mass spread out far away from the center.
It is a beautiful, elegant, geometric intersection. But looking at the equations to find that intersection raises a really annoying, persistent question. A question that plagues every student in Statistics 101. Why is the fundamental formula for the normal distribution so profoundly aesthetically ugly?
It is quite ugly.
It has a 1 over the square root of 2 pi lingering in the front, and it has a seemingly random divided by 2 shoved into the exponent. It's a cluttered mess.
To understand the ugliness, you have to understand the historical battlefield. The formula is a treaty between two warring factions of mathematics, calculus and probability. Let's look at the narrative of how this formula was forged. If you lock a calculus purist in a room and ask them to design the perfect bell curve, they want the absolute cleanest, most mathematically elegant formula possible. They want e to the power of negative x squared. That's it. Beautiful, simple, incredibly elegant to differentiate and integrate.
It sounds perfect, but there's a but.
But there is a fatal flaw for statisticians. If you take that beautiful calculus formula, e to the power of negative x squared, and you calculate its statistical variance using an advanced technique called integration by parts, the variance does not come out to 1. The variance comes out to exactly 1/2.
Hence our skinny curve. The mathematically pure curve is naturally skinny.
Precisely. Remember the error function we talked about earlier, tracking the astronomers' telescopes? It is based on this exact calculus-friendly formula. Therefore, inherently, the error function measures probabilities for a skinny distribution with a variance of 1/2. But probability purists absolutely hate this.
Why do they hate it?
Because in statistics, variance is the fundamental foundational unit of measurement. It is the heartbeat of the central limit theorem, the basis of confidence intervals, the core of standard errors. Probability purists demand that the variance of a standard normal distribution must be exactly 1, a clean, beautiful baseline integer of 1.
They want the baseline unit of the statistical universe to be a whole number.
Exactly. So a violent mathematical compromise is forced. We know we have a curve with a variance of 1/2. To stretch that variance up to a perfect 1, we know we have to stretch the x-axis outward by a factor of the square root of 2. And as we learned with our rubber band coordinate scaling, to stretch the axis outward by the square root of 2, you have to divide the x inside the function by the square root of 2.
Right.
When you square that term inside the exponent permanently becomes negative x squared divided by 2.
And because you stretch the curve sideways, you increase the physical area underneath it. So you have to squash the height down to compensate and keep the area at 1.
Right. You must divide the entire coefficient in front of the formula by the square root of 2 to squash it back down. The result of this pushing and pulling is the ugly, cluttered formula we all memorize in stats class. That straight 2 in the exponent and the square root of 2 in the coefficient. They are not random. They are the permanent, visible scars of a mathematical compromise. Calculus sacrificed its beautiful, elegant formula so that statistics could have a beautiful, clean variance of 1.
Which brings me to the ultimate mind-bending thought experiment to close this out. If this irrational number, the square root of 2, is causing so much grief, forcing us to stretch and squash our formulas, why don't we just fix the numbers? Why don't mathematicians just invent a new math system where the physical quantity of the square root of 2 is legally defined as the integer 1? If we did that, the normal distribution formula would be beautiful, the variance would be exactly 1, and everything would be harmonious.
The brilliant question. You are touching on a highly advanced mathematical concept called field extension. And strictly mathematically speaking, within a vacuum, we absolutely could do this. We could declare a brand new number system where the specific irrational quantity we currently call the square root of 2 is defined as our foundational unit, 1.
So why don't we? Why do we suffer the ugly formula?
Because there's a fatal universe-breaking consequence, and the consequence is geometry. If we redefine the universe so that statistical variance is our foundational clean integer 1, the physical world rebels against us.
How does the physical world rebel?
Think about the Pythagorean theorem. Grab a napkin and draw a simple square with side lengths of 1 inch. If you define the diagonal length of that square, which represents variance in probability space, as your clean, beautiful new integer 1, then what happens to the sides of the square?
To make the math work, the sides of the square would become some weird, messy, irrational number, 1 over the square root of 2.
Exactly. Our human counting system, 1, 2, 3, counting apples in a basket, counting fingers on a hand, is strictly linear. It is flat. But the universe operates fundamentally on squared quantities. Physical distances and physical geometry are calculated using squares. The squared plus b squared equals c squared. And errors in the statistical universe are calculated using squares. Variance is the expected squared deviation.
So the nonlinear squared reality of the universe is fundamentally, permanently incompatible with our linear human counting system.
That is the profound, unavoidable truth of all mathematics. You cannot have a clean, integer-based mathematical system for both linear counting and squared physical realities simultaneously. One of those systems must bear the heavy burden of irrationality. Those ugly constants littered throughout our most vital formulas, the square root of 2, pi, Euler's numbers, they aren't mistakes. They aren't sloppy math. They are the permanent, unavoidable friction burns left behind when human beings try to force a curved, squared, nonlinear universe into a flat, linear, integer-based counting system.
That is absolutely incredible. It makes you look at a textbook completely differently. Okay, let's take a breath and synthesize this massive journey we just went on. We started an hour ago with the medical X-ray, the deeply human desire for a clean, binary, visible answer to a complex problem. We wanted to know how to make an AI model perfectly accurate, which dragged us into the murky tug-of-war of bias and variance.
Where we realized the cruel irony that reducing your assumptions to lower bias inevitably explodes your variance, making your model gullible to noise. We crawled down into the code itself, seeing how engineers purposely use regularization to damage their models just to control that chaos. We explored information theory and KL divergence, quantifying the exact penalty for navigating reality with a flawed map.
We zoomed into the microscopic level to look at the GLU activation function, seeing how a simple, probabilistic coin toss based on the shape of a bell curve prevents billions of artificial neurons from dying in the dark. We traced the error function all the way back to 19th century astronomers trying to measure the sweep of the stars.
And we ended up here, discovering that the very mathematical formulas powering the most advanced artificial intelligence on Earth are still fighting an ancient, unresolved war between the linear way humans count on their fingers and the curved, squared physical geometry of the universe itself.
It is a lot to process, but I want to leave you, the listener, with one final, provocative thought to chew on today. The next time you are sitting at your computer, looking at an AI generating a perfectly fluent, seemingly intelligent sentence. Wait, let me rephrase that. When you see a self-driving car smoothly making a left turn through a chaotic intersection, don't just think about the millions of lines of code. Realize that deep inside its neural network, inside billions of GLU activations firing off every single millisecond, that machine is constantly negotiating a fragile mathematical truce. It is balancing the chaotic laws of probability against the rigid physical geometry of the universe, and that entire breathtaking architecture is resting precariously on the back of a single, infinite, irrational number.
It really forces you to step back and ask the ultimate question. Are the mathematical formulas we write actually discovering the true nature of reality, or are they just desperately translating a fundamentally alien universe into a rigid linear language that human brains can stomach?
That is the question to leave you with. Thank you so much for taking this deep plunge with us today. Whether you're building models or just living alongside them, keep questioning the hidden assumptions in the data around you. And remember that sometimes the murkiest, most complex waters hide the most profound truths.